Thank you very much. So yes, I'm going to talk about crosstalk effects in readout noise, and this is like a joint project done in collaboration with Philip and Oscar, who are PhD students, Joanna, who is a bachelor student, and our group leader, Michał Ośmaniec, and we are based in Center of Theoretical Physics in Warsaw. So firstly, I'm going to explain what those readout errors are, and then I'm going to provide an overview of a theoretical toolkit that we introduced to deal with those errors, and also show some results of experimental characterization of real quantum hardware. So basically, the introduction was done in the previous talk. So currently we are dealing with those quantum computing devices that are not able to perform error correction, but still, like, characterizing noise in these devices is kind of important because it can lead either to improvement in the design, or there's like a set of methods known as error mitigation techniques that maybe are not able to correct errors on their own, but still can aim at removing some of the errors in the post-processing stage. And there are various sources of noise in those NIST devices. So you can have like imperfections in the state preparation or noise associated to quantum gates that you perform. And this was as we heard in the previous talk. But here I'm going to focus on the errors that occur during the measurement stage when you measure your qubits. And the point is that if you look into some characterization data of single qubit measurement errors that do not take into account correlations, you can see that those errors are quite significant because they are on the order of errors of 2 qubit gates. So these are like examples of this plot comes from the Google error correction paper, and this is from IBM quantum data that those data are available on the internet. So this is to say that you cannot neglect easily those errors. You really need to deal with them. And just to give you a very basic intuition, what can you go wrong when you measure a quantum system? So say that you have a qubit that was prepared in like 0 state, and the ideal projective measurement in that basis should correspond to a value that will tell you that actually the qubit was in that state. But due to various reasons, in reality, there is like non-zero probability that you will actually observe the other outcome that corresponds to the other state of the qubit. And the same, of course, holds for the other state of the qubit. So now let me take those transition probabilities, and I will arrange them in a matrix that I will call lambda. So it relates ideal probability distribution to the noisy one, from which I actually sample in my using a device. Yes. And as I said in the beginning, I'm interested in crosstalk effects, so correlations. So I need to go to many qubits. And the point is that if you go to many qubits now, if you consider a generic noise model, this matrix will scale, the size of this matrix will scale exponentially in the number of qubits of your device. And this means that if you aim to characterize such a matrix, this will become infeasible for large devices. So the question is, are there some models that on the one hand capture at least some of the correlation effects, and on the other can be characterized efficiently? So a candidate class of such a models is the following. So I will assume that, okay, there are some correlations in the readout noise, but maybe those correlations do not affect all the qubits simultaneously. So there will be some groups of qubits that are correlated, for which this readout process is correlated. And I will decompose the whole noise matrix into tensor product over those matrices describing correlations for different groups of qubits. I will refer to those groups as clusters. And I will put additional restrictions, so I will say that like the size of the cluster will be limited. So there will be a maximum number of qubits that can belong to a cluster. So now the task is to have a procedure that will efficiently output such a noise model from the experimental data. I do not know which qubits should belong to which cluster, but I only know that there are clusters and they have some maximal size. And like this is the outline of the procedure that we proposed. So firstly, you have this experimental kind of part in which you need to design and actually implement experiments on a device that you want to characterize. Then there is this data post-processing stage. And at the end of the stage, you will get the noise model, the reconstruction of the noise model. And finally, you know, just because we can reconstruct some noise model, it doesn't mean that it will be useful or accurate. So we want to verify how well do we capture those crosstalk effects in the readout noise. So this will be the third stage. I will now go through all of those steps. So the first part is this experiment design and implementation. So we used the so-called detector overlapping tomography, which is like a clever parallel way of doing partial characterization of the measurement process. And our result is that we know how this scales. So say I have an n-qubit device and I want to characterize all measurement operators acting on k qubits up to some error. Then I know that the number of experiments I need to perform scales exponentially in k. So k corresponds to the totality of noise, but only logarithmically with n. And this means that the whole procedure can be efficient. So it was firstly introduced by Jordan Kotler and Frank Wilczek in context of quantum state tomography, and we then adapted it to the context of, let's say, detector tomography. And you can say that like this method fits into like a broader randomized measurement toolbox that was initiated really 10 years ago by Jens Eisert and coworkers, and recently has been also developed. Yeah. Okay, so what kind of experiments do we really need? So we need like n circuits. This number is dictated by the previous formula. And each circuit is constructed in the following way. So I just need a single layer of 1 qubit gates that will prepare Pauli eigenstates. And I choose those gates at random. And this is the collection that I need of experiments that I need to perform on a device. And just to give you an idea, why do I need to do this in this like parallel way, this overlapping way? So say I have a device that contains like 127 qubits and the locality that I'm interested in is like 2. So then if I would do it naively, I will need like order of hundreds of thousands of experiments. And if I do it in a parallel, I need just like hundreds of circuits. So this is the only way to go if you want to deal with large devices. Okay, and at the end, when I do these experiments, then we perform, then what we get is like this kind of reduced POVM, so a measurement operator describing measurement on those like k qubits, and this is the basis for all further analysis that we do. And now we want to find those clusters of qubits that are correlated when it comes to the readout noise. So the first thing that we do is we quantify like pairwise correlations in the readout between different qubits. So I take qubits I and j, and I investigate the following thing. So I fix this input state on qubit j, and I check what is the resulting marginal probability distribution on qubit I, and how does it depend on the input state of the qubit j. So really I have like two marginal probability distributions corresponding to two different input states on qubit j, and I quantify how different they are. And this tells me how what is the influence really of input state of the qubit j on the measurement outcomes that I see on qubit I. Yes, and let's say that this coefficient is equal to 10%. So this means that those two probability distributions different by 0.1 in total variational distance. So now I can, perform those experiments and calculate those correlation coefficients. So here are the results for IBM Washington, and this is the layout of the device. So, and those like lines here are the correlation coefficients. So we plotted them above some thresholds. So the threshold is like 2%. You can see that a bunch of qubits are correlated. But also, you can notice that some correlations are really strong. So those correlations here, they are on the order of 20%. So these are pretty significant correlations. We did the same for Rigetti, and the results are here. So please notice the other scale. So for Rigetti, those correlations tend to be like higher, and also we detect some pretty significant high correlations, like on the order of even 30%. And maybe the better way to visualize this is to have a cumulative histogram. So here is the fraction of all correlation coefficients. And here is the value, actual value of correlation coefficients. So this is to say that, for example, like 97% of coefficients for IBM Washington, this is this green line, are like, are like below 0.5. So they are quite small, but you can also see that there are like some pretty significant correlations in the end. And also this plot demonstrates that those correlations for Rigetti, they tend to be in general higher than for IBM. Yeah, and so now we calculated all those correlation coefficients. We have them. So what we do now, we basically run a clustering algorithm, because from those correlation coefficients, we really want to reconstruct this the noise model. So you can think that this is like a community detection problem, but there is like one additional thing here, namely, like in social networks, those algorithms tend to increase your social your contacts as much as possible, but here we have these restrictions. We don't want those groups, those clusters to get too large, so we need to take into account that. And at the end of the stage, we get this model that describes noise in our device. Okay, so we have a model, but now the final question is it really accurate? To what extent? So in order to do this, we did like some benchmarks, and one of the benchmarks that we did is we chose some like local Hamiltonians that are composed of Pauli Z operators, and so then we can easily find like eigenstates of that Hamiltonian and also eigenvalues, and then so we know what the energy of this eigenstate is. But we ask our device to prepare that eigenstate, and we measure it in order to estimate the energy like on the device. And then we put this additional step, so we mitigate these readout errors by simply finding inverse of the noise model. And in this way, we obtain this like estimate energy. We have this value of energy estimated from the experiment, and we compare it to the true value of that eigenstate. And in order to have like a fair comparison between different devices, we take like the absolute difference between the two and divide it by the number of qubits. So here are the results for IBM Washington. So the green line corresponds to the procedure that I just described. The red line, these are like unmitigated results. And this is again a cumulative histogram, because we chose like a number of different Hamiltonians to see how the method performs. So you can see that there is like improvement in doing this. And also for reference, there is this purple line. So this purple line is just like a noise model constructed out of single qubit errors, so they do not take into account any correlations in the readout process. So like doing mitigation this way is also beneficial, but you can see that like taking into account correlations in that way leads to better results. And the same conclusion can be made when looking at data collected at this Rigetti Aspen M1 device, and the difference here is even bigger than for IBM. So the errors at Rigetti tend to be higher. Okay, and this is basically all that I have to say. So I wanted to convince you that there is efficient method of characterizing those readout errors, at least like partially, to a given locality, and that error mitigation can improve quality of the results that you get. And there is like an open source package that we develop. So if you want to do this, you can use it, but please don't do it today because there is a major update coming that will have more functionalities. So please wait a couple of weeks and then you can do basically all what I said quite easily in Python. Thank you very much for your attention.